Okay, Alberto. Floor is yours.
Thank you. So, hello, good morning. I am Alberto Solera. This is my second year at the PhD program. And I'm working under the supervision of Stefano Dicetti and Carlos San Miguel about active flow control methods for with data-driven algorithms for flow control. We know that transport represents a big part of greenhouse gas emissions, at least in Europe, in the developed countries, and is one of the main contributors of air pollution in cities. Among them, drag is one of the main sources of energy losses in transport, about 20% in trucks. And there are some classical optimizations to reduce drag in vehicles in general that usually involve geometrical modification that is not always possible or desirable because, for example, it occupies extra space or decreases the payload of the vehicle. So we want to apply new possibilities using data-driven active flow control to efficiently, using less energy than the savings achieved, build systems that work in constrained environments where we can, for example, we can't change the external geometry of the vehicle and work in variable conditions, for example, different velocities or angles of attack. In active flow control, machine learning can be used for different areas. It can be used to build reduced order models, as we were talking about, to keep only the essential information and work in that reduced space. We can use it to estimate that reduced representation from a few sensors. Practical applications needs to rely in practical sensors. And of course, we can use it to learn complex flow control algorithms that optimize the use of the information from the sensors to optimally control or quasi-optimally control the available actuators. This is a current trend in academia right now, and there are expected applications in maybe near or mid-term in industry. The main research question for my PhD are whether a reduced order representation still contains meaningful information for control algorithms to work. We need to test if we can build that mapping between the sensors and the reduced representations that relies on a complete state of preservation. And we have to try to build a reduced order model that accepts a control input and is suitable to work in a model predictive control or reinforcement learning framework. These are the two frameworks that we are considering for the thesis. And we can apply machine learning, for example, in the model part of the MPC or environment to pre-train a reinforcement learning agent before deploying it to an experimental or real problem. We can apply the machine learning algorithm for the estimators, state estimation in MPC, or the interpreter in the reinforcement learning framework. And of course, we can apply it for the reinforcement learning agent. The activities for the second year have been, first of all, finishing the first publication, major milestone. And we have been continuing to work in reduced order models. First of all, for model decomposition and prediction, that's the topic of the paper. And now we have a work in progress for state estimation and sensor selection. And also a work in progress about a reduced order model that can be applied to propagate the system state in sensors space. So the first publication, this is a reducer model for the dynamics of a chaotic flow, a 2D chaotic flow. Here we use a beta variation autoencoder to compress the full flow information into a small latent space about size 10 to 20, and we compare the latent space with the PhD, both in terms on space and modes and characteristics of temporal modes, for example, the spectra. And then in that small dimensional space, we apply a transformer to propagate the state into the future. And we find that it is able to generalize, which is something not found usually in the related bibliography. There are some tricks in most of the papers. And we find that although the prediction diverges from the true modes as expected in a chaotic system, the characteristics of the predictions keep the system dynamics. We explore the Poincare maps and the probability density functions of the predictions and are comparable to those of the true modes. This is the work about the state estimation problem, where we use the fluidic pinball test case. We use pressure sensors in the surface of the cylinder to a series of measurements of the pressure sensors to estimate the current point in the latent space of a beta variation autoencoder. So we map from sensors to the previous work on beta variation autoencoders. And we also apply a first layer in the state estimation network to select only the most valuable sensors, so we can perform the prediction using only, for example, 10 sensors. It's an optimization of the number of sensors. Now we are working on the coupling between the CFD simulations and control algorithms. Right now we have built some data sets with open loop actuation, and we have preparing the framework for closed loop control. It's based on GPrecise, an open source implementations that is a wrapper for OpenFOAM that converts it to a GIM environment. So it's the usual environment for reinforcement learning problems. It's a toy model of a 2D track where we have pressure sensors in the surface of the track. We actuate two jets at the base of the track, and we explore chirp and random actuation cases to prove the actuation space. Using this dataset, we built a predictive and recursive sensors to drag coefficient model that uses sensors and control past points to predict the next sensors and drag coefficient point. So we can apply it recursively and use it in a MPC or RL framework. The planning is to continue work on reduced order models with control input, to apply control in low-dimensional state spaces. And the main challenges are this coupling between CFD and control algorithms in Python usually for closed-loop control. And this is a challenge in simulation, but the real problem is the implementation in experimental cases where we have the problem we were talking about of the tight time constraints. These are some related reference for my PhD. And the achievements so far are, of course, the Nature Communications paper, a related paper in International Journal of Heat and Fluid Flow that applies more or less the same algorithms to a more complex Turing flow, and we analyze the parameters of the model. And well, we also presented a poster in a small conference at INTA. And that's all.